Good morning all. My name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is Computer Architecture. Today I am discussing about problem solving on arithmetic operations. So, what are the arithmetic operations? So, we are also doing the arithmetic operations in pipeline process. So, before going to arithmetic pipeline, we have to go for pipelining. Pipelining is a technique of decomposing a sequential process into sub-operations, with each sub-process being executed in a special dedicated segment that operates concurrently with all other segments. Each segment performs partial processing dictated by the way the task is partitioned. The result obtained from the computation in each segment is transferred to the next segment in the pipeline. So, in the pipeline, we are also performing arithmetic operations. So, what are the arithmetic operations means? Addition, subtraction, multiplication, division, increment, and decrement. So, these are the arithmetic operations to be performed. So, what is the technique here I am using means pipeline method here I am using. So, it is a technique for decomposing a sequential process into sub-operations. So, what is the main operation? How many registers we need? How many variables we need? So, we have to take as a process and we have to take how many sub-operations we need for that one. So, one example we will think about this one. And each segment performs partial processing dedicated by the way the task is partitioned, and the result obtained from the computation in each segment is transferred to the next segment in the pipeline. The final result is obtained after the data have passed through all segments. Each segment consists of an input register followed by a combination circuit. A clock is applied to all registers after enough time has elapsed to perform all segment activity. The information flows through the pipeline one stop at a time. So, when the pipeline is the process, so pipeline is a process or operation, we are converting to the sub-operations. Suppose I'm going about the A into B plus C. So here, how many variables I need? Here I am taking A, B, C. So 3 registers. So we are taking as a 3 registers, and it is a multiplication and addition. So A into B, one operation, and after the getting of result, A into B I am taking as X. So this I am taking as a Y. So I am taking as a X plus Y. So how many sub operations we need? A into B is one operation, and I am taking C is variable one operation, and when I am adding after getting the A into B result, this result value is added to this one. So we need 3 segments or 3 sub operations. 3 segments or 3 sub operations we need. So what is the final result? So I'm getting here X plus Y equal to Z example. So Z is the final result obtained after the data have passed through all segments. Each segment consists of all input registers followed by an combination circuit. So each segment, A into B is one segment and C is another segment, and this addition 1 plus 2, that is another segment. So here 3 segments are there. These 3 segments are using combination circuits with clock pulse is applied to the registers. And what is the elapsed time to perform all the segments activity? The information flows through the pipeline is a one stop at a time. So A into B plus C into D. So here I am taking one segment. So what is the output of B? A into B is 1 X, and C into B is another segment 2, and it is I am taking as a Y. So after getting the result of A into B, that is X, after getting the result of C into D, that is Y, and finally X plus Y equal to Z. So X plus Y equal to means Z, it is one segment. So it is a segment 3. So 3 segments or 3 sub operations. So A into B plus C into D is a one operation. This operation we are dividing as a 3 sub operations or 3 segments. Example, perform A into B plus C for I equal to 1, 2, 3, so on 7 using pipeline method, and the sub operations performed in each segment are R1 to AI, R2 to BI. So here I am taking R3 to R1 into R2, R4 to R4 to CA, and R5 equal to R3 plus R4. So it is the one question. Here, what is the question is here? A into B plus C. So here I am taking AA, BA, CA. So I is a variable. Here I am taking I equal to 1, 2, 3, 4, 5, 6, 7. So 7 possibilities of A1, A2, A3 like this. So that means AI equal to, that means A1, A2, A3, so on A7. BA means B1, B2, B3, so on B7. And CI means C1, C2, so on C7. So perform A into B plus C using pipeline method, and what are the sub operations to be performed in each segment. So here I am taking 3 segments or 3 sub operations we need. Segment 1 A to R1, that is means I am calling one register AA equal to R1, and I am calling another register for B. I am calling another register for C. But here first I am not calling C now. First, why? Because first I will be perform A into B. So R1 A equal to R1 and B equal to R2. So I am multiplying with R1 and R2. R1 and R2. So after the multiplication of R1 and R2, the resultant value should be stored in R3. Here that means R3 is nothing but R3 tends to R1 into R2. So what is the now? This is called R3. So C4 I am taking as a R4. So it is R3. CA equal to R4. So now R3 plus R4. R3 plus R4. So what is the resultant value? R5. So after the addition of R3 value and R4 value, the resultant should be stored in R5 register. So already we know that R3 is nothing but A into B plus R4 is nothing but CI. So A into B plus C, that equal to, what is our final answer? Here I am taking R5. So R3 plus R4 equal to R5. How many segments we need? Total we need 3 segments, but that means 3 sub operations should be performed in the pipeline method. It is a flow chart of arithmetic operation of this example. Example of pipeline processing. Here I am taking AI into BI plus CI. So AI equal to R1 register, BI equal to R2 register. So AI equal to R1 and BI equal to R2. So I am multiplying AI into BA. That means R1 into R2. R1 into R2 and multiplier. Multiplication is I am taking a multiplier, and the resultant value is stored in R3. So R1 into R2 value should be stored in R3, and after getting the R3 I am calling CI now. CI equal to, now I am taking as a R4. So CI equal to R4. This R3, R1 into R2 value is R3 and the CI value equal to R4. So I am taking addition of this one, R3 plus R4. So what I need for plus means adder. So R3 plus R4. R3 plus R4 resultant value should be stored in R5. So R1 equal to AI, R2 equal to BI, R1 into R2, that is a multiplier, and the CA value stored in R4. So R1 into R2, R3 equal to R1 into R2, and R4 is calling as a R4. And what is the adder means now? Adder means R3 plus R4, R3 plus R4. The resultant should be stored in R5. The content of registers in pipeline example. So already we discussed here up to now A into B plus C. How many segments? In this slide we have discussed How many segments I need? Here we need 3 segments. And in this, we are getting what is the flow chart and how many logic gates we need. Here multiplier is 1 logic gate, adder is I'm taking. So how many logic gates we need? 2 logic gates and 3 registers. Here I'm taking how much is going on and what is the clock pulse of this operation. So content of registers in pipeline example. Segment 1, segment 2 and segment 3. So how many clock pulses we need for this operation? First I'm calling so AI equal to R1, BI equal to R2. So first I am taking A means R1 R2. So it is R1 and it is R2. Okay, that one. AA means first I am taking A1, here B1, after that A2, B2, so on A7 and it is a B7. So first I am taking A1 and B1 in the segment 1. So A1 equal to R1 and B1 equal to R2. So these functions I am calling as AI R1, BI R2. So R1, R2 I am taking as a AI, BI and the segment 2 R3 and R4. Okay, it is a segment 2, but in the segment 1 I am calling 2 registers, that is A1 equal to R1 and B1 equal to R2. In the segment 2, what we have to do after calling these 2 registers in place of A and BI, I am multiplying here, that is in the segment 2. So A into A1 into B1 equal to R3. Already in the previous also we discussed. A into B equal to R1 into R2, that is the R3. So R1 into R2, that is I am taking as a R3. So A1 into B1, that is in the R3 and R4 I am calling as a C1. So A1 into B1 stored in R3 and C1 I am taking as a R4 register in the segment 2. In the segment 3 what will happen now? A1 into B1 is completed in the R3 and C1 also called R4 equal to in this, and in the segment 3 what will happen? I am adding A1 into B1 value according with C value. So it will be stored in segment 3 in R5 register. Next, first clock pulse A1, B1. In the clock 1 I am calling as A1 and B1. A1, B1 clock called clock 2 A1 into B1. A1 into B1 in the clock 2 and also called as C1 now. In the clock 3, what happened? A1 into B1 is completed and C1 is added here. So in the clock 1, 2 registers are called. In the clock 2, multiplied and clock C1 value is called, and clock 3, clock 2 multiplication is completed. After the multiplication, we are getting this value A1 into B1, and in the clock 3, we are adding with C. That is the 3 segments, 3 clock pulses, like this. And the next clock 4, again, in the clock 2, A1, B1 are called now. So in the clock 2, we are not wasting time. Continuously process is going on. In the clock 2, A1 into B1 is going on, and parallelly A2, B2 is also called. A1, B1 is completed. Now what is the next task? A2 and B2. So in the clock 2, A1 into B1 is going on, and accordingly A2, B2 also called. So A2, B2 is called in clock 2, and in the A3 in the clock 3 pulse, A3, B3 also called, and parallelly A2 into B2 is going on, and C2 also called, and A1 into B1 plus C1 is going on. So how many segments are going on here? In the clock 3, 3 segments. In the clock 2, 2 segments. In the clock 1, 1 segment. What is the 1 segment? A1, B1. In the clock 2, 2 segments. A2, B2 is called, and A1 into B1 is completed. In the clock 3, A3, B3 is called, A2 into B2 is completed, and A1 into B1 plus C1 is also going on, like this. So, how many segments? 3 segments. How many registers? 5 registers. How many operations, sub-operations we need? 3 operations. 3 sub-operations. That is segment 1, segment 2, segment 3. R1 into R2 and R3 is calling, and in the segment 3, R1 into R2 plus, R1 into R2 plus R5. Why? Because R1 into R2 equal to R3 and R4 this is calling as a C. So here in the segment 3, what is going on means R4, R3 plus R4 that equal to R5. So it is about the arithmetic pipeline, and any operation that can be decomposed into a sequence of sub operations of about the same complexity can be implemented by a pipeline processor, and the technique is efficient for those applications that need to be repeat the same task many times with the different sets of data. A task is a total operation performed going through all segments of a pipeline, and the general structure of a 4-segment pipeline is as shown in the below figure. So any operation that can be decomposed into sequence of operations about the same complexity into a implemented by a piping processor. Any operation I am taking A into A1 into B1 plus C1 into D1. So any of the operation, it is completely one operation. This operation can be decomposed. The decomposed means we are dividing as a into B is one and C into D is another one, and A into B plus C into D is another one. And it is a complexity of the pipeline processor, and the technique is efficient for those applications that need to repeat the same task many times with different sets of data. A task is the total operation performed go through all segments of a pipeline. So what is the total operation? A into B plus C into B. This total operation is performed through all segments. Segment 1, segment 2, and it is a segment 3. Three segments of a pipeline, and the general structure of 4-segment pipeline is as shown. Previously we discussed only 3 segments, 1, 2 and 3. Now we are going for the 4-segment operation. So what is the 4-segment operation? How it is there? It is a block diagram of 4-segment pipeline. It is a figure 1. So input segment 1 I am taking as a register 1, and in the segment 2 I am calling register 2, segment 3 register 3, segment 4 register 4. So every segment, maybe suppose I am taking here it is R1, in the segment 2 R1 multiply with R2, maybe in the R3 R1 into R2 plus R3. Here I am taking example, say in the segment 2 R1 into R2, in the segment 3 R1 into R2 plus R3 maybe, and here what is the final result? It will be stored in R4 like this. Arithmetic pipeline. Pipeline arithmetic units are usually found in very high-speed computers. Arithmetic pipelines are constructed for simple fixed point, floating point arithmetic operations. To understand the concepts of arithmetic pipeline in a more convenient way, let us consider an example of pipeline unit of floating point addition and subtraction. Here I am taking only 4 segments and 4 registers, 4-segment pipeline. Here I am taking these 4 segments as one arithmetic pipeline operation. So what is the arithmetic pipeline? Pipeline arithmetic units are usually found in very high-speed computers. Arithmetic pipelines are constructed for simple fixed point and floating point arithmetic operations. Simple fixed point and floating point. Floating point means 1.026 into 10 square, example, or 1026 into 10 square. So it is a floating point. It is a fixed point. To understand the concepts of arithmetic pipeline in a more convenient way, let us consider an example of a pipeline unit for floating point addition and subtraction. So arithmetic pipelines with simple fixed and floating point. To understand the concepts of arithmetic pipeline in a more convenient way, the example of a pipeline unit is floating point addition and subtraction. We are taking as one example as floating point arithmetic operation. Example 2, perform the following floating point adder operation using pipeline. X equal to A into 2 power A, Y equal to B into 2 power B. The two normalized floating point binary numbers defined as capital A into 2 power A and B into 2 power B, where A and B are two fractions that represent the mantissa and exponents. So it is a question to perform the following floating point adder operation using pipeline. Floating point means we have to take floating numbers, and here one example, x equal to a into 2 power a and y equal to b into 2 power b. So it is nothing but it is in the form of mantissa and exponent. So these are calling as exponents, and it is a mantissa. So mantissa and exponent and exponents. So a into b are the two fractions that represent the mantissa, and small a and small b are the exponents. The combined operation of floating point addition and subtraction is divided into 4 segments. Each segment contains the corresponding sub-operation to be performed in the given pipeline. The sub-operations that are shown in the 4 segments are: compare the exponents by subtraction, align the mantissa, add or subtract the mantissa, normalize the result. So in this example, simply they are giving one question, but what are the conditions are there for this question? Before solving this, we know that what are the conditions, and we have to satisfy that conditions, then only we can get the result. So what is the first condition in this question? Is it any mantissa is there, or is the exponents are there? Yes, a and b are the mantissas, and small a and small b are the exponents. Okay, so one clarity we got, it is a mantissa. Next, compare the exponents by subtraction, align the mantissa, add or subtract the mantissa, normalize the result. First, compare the exponents. What are the exponents here? A into 2 power a, b into 2 power b. So we have to take these exponents should be balanced and align the mantissa. Suppose what is here, a equal to, suppose example 2.023, here b equal to 0.2023. Is it same? No. Here one integer value 2.0, but here there is no integer 0. So we have to balance. So exponents balancing is completed. Next we'll go for the mantissa balancing and add or subtract the mantissa. After balance of this exponents and mantissa, we have to go for addition and subtraction and normalize the result. The following block diagram represents the sub operations performed in each segment of the pipeline. So what are the exponents and mantissas? So in the question, capital A and capital B are the mantissa, small a and small b are the exponents. So here small a and small b are the exponents, capital A, capital B are the mantissas. So we have to compare these. Then I need one register to compare. Is it any a greater than b, a less than b, or equal to b? How can I know a greater than b, a less than b, or equal to b? So for this comparison, I need one register, that is I am taking as or, to compare the exponents by subtraction. Here suppose 10 square, a equal to 10 square, b equal to 10 cube. So it is a 2 and it is a 3. So we have to comparing which one is larger or equal. Equal means no problem. If less than or greater than, we have to compare and balance. And in the segment 1, we are comparing. In the segment 2, we are choosing the exponent. We have to choose. Both are have to take same. Here a equal to 10 square and b equal to 10 cube. So we have to take a equal to 10 square and b equal to 10 square, or a equal to 10 cube and b equal to 10 cube. So we have to choose the which exponent you have to satisfy. Next, segment 3. So if I want to choose this exponent, definitely I need one register. And segment 3, we are adjusting the exponents. So how we adjusting? 10 square is changed to a 10 cube, or 10 cube changed to 10 square. How we adjusted? As adjusted in the segment 4. Like this, in the mantissa, align the mantissa is there 0.2023 and another one is a 2.2023. So we have to adjust. So I need one register to align the mantissa, and after adjusting this one, add or subtract in the mantissa, I need one register to assign and normalize the result. The result should be normalized in the one register and getting the output. So compare the exponents by subtraction. The exponents are compared by subtracting them to determine their difference. The larger exponent is chosen as the exponent of the result. The difference of the exponents, that is 3 minus 2 equal to 1, determine how many times the mantissa associated with the smaller exponents must be shifted to the right. So here x equal to 2 power a, y equal to 2 power b. So x equal to, I'm taking x equal to a into 2 power a, y equal to b into 2 power b. So a and b 0.9504 and b is a 0.8200. So here 2 power a equal to 2 power q, 10 cube, 2 power b I'm taking 10 square. It is one example I'm taking. So 3 minus 2 equal to 1 determines how many times the multiplicity is associated with the small exponents. So first the exponents are compared by subtracting them to determine their difference. The larger exponent is chosen as the exponent of the result. Here I'm taking 0.95. Here also 0.9. So Montissa is balanced and exponents have to be balanced because it is a 10 cube and it is a 10 square. So a comparison is completed. Now align the Montissa. So the Montissa associated with the smaller exponent is shifted according to the difference of exponents determined in segment. Here I am taking 0.9504 into 10 cube. Here y equal to 0.08. Here 0.9. Here 0.800. But here 10 square. Here 10 cube. So for this purpose, I am changing as 0.9504 into 10 cube here. But here 10 square is changed to 10 cube. If I am changing this 10 cube means it will become to shifted to here 0.08 0.08200 into 10 cube. Now these exponents are also balanced. Now add Montissa. Now I am performing z equal to x plus y. Why I am performing like this means Montissa and exponents are balanced. So 1.0324. 0.9504 and y equal to 0.0800. Zero point zero eight two double zero into 10 cube. Now 1 2 3 4 digits 1 2 3 4 4 2 5 plus 8 13 9 plus 5 1.03241 1.0324 into 10 cube and again normalize the result. Why? Because here z equal to 0 point, y equal to 0 point. So result also we are expecting 0 point, but here I am getting the result as 1.03. So I am expecting as 0.0, but here I am getting 1.0. So we have to again normalize the result. That is z equal to 0 point. So z equal to this one is shifted to here. So in place of 1, I am taking 0. 1 is shifted to here 10324. So 0 point in place of this one, I am getting 1324 into 10 power 4. 10 cube is changed to 10 power 4. So it is a floating point of x equal to a into 2 power a and y equal to b into 2 power b. So comparing the exponents by subtraction and align the Montissa in the step 3, add Montissa in the step 4, normal is the result. Example 3, using arithmetic pipeline, perform the following addition and subtraction of floating points on a pipeline unit. So we have to take the pipeline unit method and we have to perform the addition and subtraction in the floating points. So consider the two normalized floating point binary numbers as the input of floating point adder pipeline. They are defined as p equal to u into 2 per u, q equal to v into 2 per v. So we have to take our own example to perform addition and subtraction in the floating point numbers with the performance of pipeline unit method. So I am taking here p and q are the two variables, and the minimum two variables I need for addition and subtraction. Addition or subtraction. 0.9800 into 10 square, 0.7900 into 10 power 1. It is one example I am taking. Considering an example, u and v are the exponents. The capital V and V are the Montissas. So U and V are the small u and V are the exponents, capital U and V are the Montissas, and the process of floating point addition and subtraction is divided into 4 parts. Each segment of the pipeline is dedicated to the specific sub operation, and these sub operations include compare the exponents using sub operation, align the Montissa, add and subtract in the Montissa, normalize the result. In the exam, any of the question, if you are getting like addition and subtraction or the arithmetic operation using pipeline with the floating point numbers, definitely we have to follow these 4 conditions. Compare the exponent using subtraction, align the Montissa, and add subtracting the Montissa, and normalize the result. So we have to follow these 4 rules. Based on the difference of exponents calculated in the first segment, the Montissa associated with a smaller exponent is mode P equal to 0.9800 into 10 square, Q equal to 0.07900 into 10 square. Adding the Montissa step by step. The third segment involves the addition of 2 Montissas, that is P and Q. Addition of these P and Q I am taking as OR. So P is one variable, Q is one another variable. We have to add P plus Q. The resultant is I am taking as a OR. So P is one register, Q is another register. The resultant value stored in OR register. So OR equal to P plus Q, that is 0.9800 plus 0.0900. So I'm taking here 10 square. Why? Because here 10 square, here 10 power 1. So both exponents should be balanced. So here I'm taking both are 10 square I'm taking. So that is the reason I'm changing the values as 0.9800, 0.07900, like this. 0.9800 into 10 square, 0.079 into 10 square, 0, 9, 15, 1.0590 into 10 square. It is a or equal to P plus Q. But again, what is the fourth condition? Normalize the result. The result is 1.0. In the question is P equal to 0.9, Q equal to 0.0. But answer is we are 1.0. But we have to change it to 0. Something. Normalize the result. The process of comparing the exponents by subtraction. The first step involves calculating the difference between the exponents by subtracting them. And the larger exponent is selected as the exponent of the result. And the difference exponent is a 2 minus 1. What is the exponent value? We are taking as a minus b. And needs to shift it to the right. And understanding the normalize the result. After normalizing the result will be expressed as capital R equal to, previously we have 1 point, but I am taking as 0.1059 into 10 cube. Previously 10 square. It is the sub operation performed in the each pipeline. So it is a flow chart of arithmetic operation. I am taking as exponents of x and y, and for the comparison I am taking register OR. For Montissa x and y, for the comparison we are taking one register OR, and comparing the exponents by subtraction. So exponents I have to take, suppose a equal to 10 square and b equal to 10 cube. It is 10 square and it is 10 cube. So we have to compare first which one is larger. And for this comparison we need one register. For comparison operation I am taking segment 1. In the segment 2, choose the exponent. So we are compared. It is a 10 square and 10 cube. So which one is chosen? So I am taking as a both are 10 cube or both are 10 square. So what is the choosing final? That is the segment 2. In the segment 3, after choosing the exponent, are you taking any register? As I am taking one register for final choosing one. And in the segment 4, adjust the segment, adjust the exponent. If I am taking both are 10 cube or both are 10 square. And Montissa also I am comparing with one register OR and align the Montissa in OR register. And after the aligning of this one, I am taking suppose 0.01. Here also 0.02. So aligned both are same, and after the alignment I am taking as add or subtraction with the register and normalize the result. Results also I am getting 0.0 something only, and this register I am calling as a OR register. So these are the references. So today we discussed arithmetic pipeline, that is the arithmetic operations of addition, subtraction, multiplication, division, increment and decrement with the pipelining process. So here I'm taking one example of pipeline A into B plus C. Here I'm taking segment 1, segment 2, segment 3. In the segment 1, all the variables I'm taking as a calling function are each register A equal to R1 and B equal to R2. In the segment 2, R1 into R2 multiplied and C is a one calling register R4. In the segment 3, the resultant of A into B and plus C is added in the segment 3 and the resultant value stored in R5. It is a flow chart of arithmetic operation R1 into R2 using multiply stored in R3, CA equal to C1 equal to R4. So this resultant value R3 plus R4, that is a R5. It is a clock pulse from 0 to 7, or I am taking as a 1, 2, 3, 4, 5, 7. Why? Because here I equal to 1, 2, 3, so on 7. So clock pulse also we have to take from 1 to 7. 1 to 7 we have to take the clock pulse. Why? Because here also I equal to 1, 2, 3, 4, 5, 6, 7. So up to now I am started with this 7. So it is a clock pulse with 4 segments: S1 R1, S2 R2, S3 R3, S4 R4. Arithmetic pipeline. These are two types: simple fixed point, floating point. It is example for floating point addition operation using pipeline method. So we have to take four levels are there, 4 techniques or 4 methods we have to follow. Compare the exponent by subtraction, align the mantissa, add or subtract the mantissa, normalize the result. These are the 4 steps. It is a flowchart, and this is the comparing operation of exponent. Step 1, step 2, align the mantissa, step 3, add the mantissa, step 4, normalize the result. Example 3, using arithmetic pipeline for perform following addition and subtraction of floating point using pipeline method. Here I am taking one example is our own. P equal to U into 2 per U, Q equal to V into 2 per V, P plus U, we are calling as P plus U, P plus Q I am taking as a or. What are the conditions? Comparing, aligning and adding, subtracting mantissa, normalize the result. So the process of comparing the exponents by subtraction, understanding the normalize of the result, and it is a flow chart. These are the references for this topic. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.